my lecture today. And of course, I hope you enjoy your spring break. Okay, I want to welcome you to another exciting statistical topic. Let me say, this week I'm going to release midterm 2 practice questions. Of course, we are counting down to midterm 2. But the focus today is basically going to be on the final conclusion on the mixed effect models that we start, because Wednesday we're going to start a new topic. So we are still on what I call a mixed effect model. I call that part 2. In the outline today, I'm basically going to walk you through two-way mixed effect. Okay, of course, the other time we focus on, situation where we have intercept and one factor that is also random. Well, of course, we can also call that a mixed effect. But today we're going to focus on two-way, where we have two factors. And not only that, we also going to investigate assumptions. You know, what makes a model to be valid is when assumption hold. And of course, I'm going to walk you through some example. Okay, of course, I've presented a mixed effect model to you the other time. By mixed effect model, of course, we're trying to say that the observations can actually be written in terms of fixed effect plus the random effect plus the error. So what I'm trying to show you now is just the general model for mixed effects. Okay, you know, of course, I've walked you through the mixed effect model before, but our major focus today will basically be on how do we assess assumptions, the model assumption, because assumptions are very, very crucial. If you take a look at what I'm showing you now, situation where we have, let's start from one-way analysis of variance, where the factor that we have is random. Of course, by now, you know what we mean by saying that an effect is random. It means we are actually select a random sample of levels from the population. Now, if you take a look at what I'm just displaying now, we actually expect that the factor that is random, we have its variance. And of course, the error in a model, we also have its variance. And that is what you can see now. And we have an assumption that the probability distribution of them have to be normal. That's what you see that I'm displaying on the board. They have to be normal. And of course, we expect the residual to have a constant variance. If you take a look at the alpha high follow normal distribution with a mean 0, and the variance is sigma square alpha. And error follow normal distribution with mean 0 and the variance sigma squared. What if in a situation where there's a violation, how are we going to know? Of course, we have a way to know if there's a violation. And if there's a violation, then it means we may not be able to trust our model anymore. Something needs to be done, which I'm going to walk you through today. Okay, so in the example that I've given you before, there was a particular data that's on BASH. We got two different forms of that data. We have we have a die stuff too. We have a die stuff. But the one of the die stuffs too, the reason why we don't want to use that, if you look at the result that we got before, the variance associated with the BASH was 0. And that is why we don't want to consider that. We want to consider the one where the variance exists. Now take a look at what I'm going to be displaying now. I'm actually using a diced of data. Okay, when you take a look at this, we are considering one factor experiments, and that factor is Bash, and the levels of Bash that we choose them at random, and that actually qualify Bash to be a random effect. Now, if you take a look at what I'm trying to show you now, this is a code, arrow code with the arrow output situation where we are considering one factor, one way analysis of variance, and the only factor in the model is Bash, and it's random. And that is why in the output, you're basically going to see two forms of the output. One is going to be random effect. The other one is going to be fixed effect. The one that is fixed effect is just the intercept. Of course, every statistical model we normally specify the intercept. Now, when you take a look at the random here, what is the variance of Bash? The variance of Bash is 1764, as you can see, with a standard deviation of 42.00. What is the variance of the residual? The variance of residual is 2451. What can you see? The variance of the Bash and the variance of the residual, they are not the same. Okay. And of course, knowing the variance of a system. Now take a look at this. When we are dealing with a random effect, we're always going to consider the variance. In statistical analysis, I know some people may refer to variance as nuisance, or variance as something that we want to minimize. It is not all the time that our focus is going to be on that. If I really want to know how system work, I'm going to say that again. If I really want to know how system work, then I need to know the variance associated with each component in a system. I'm going to say that again. If we really want to know how system work, of course, we need to be able to identify or quantify the variance associated with the components of the system. Okay, and that's why you see us analyzing, focusing on the variance in the random effect. Now, take a look at this. And of course, we actually also believe that there's going to be, because the assumption here is that the intercept is not constant, but the slope is constant. And that is the reason if I have 6 levels of batch of a factor, I'm going to have 6 different intercepts, which means intercept is not the same. Intercept of a particular level of a factor is different from another level of that factor. That was not the assumption in the fixed effect model. In the fixed effect model, you have a constant intercept across the levels of a factor. But in the random effect, the intercept is not the same. Of course, when we're considering in this course a situation where intercept changes and slope remain the same. In regression analysis, where we are looking at regression with random effect, we could also have situation whereby intercept may remain the same while slope varies. We can also have situation where intercept changes and slope also changes as well. But the one we're going to focus here is the one, it is only intercept that change while slope remain the same. And that's why you are seeing for 6 level of batches that we consider here, we're basically going to have 6 intercepts. That is what I'm displaying now. Now, of course, I've walked you through all this. But you know what we want to do now? How do we tell whether a model that we actually use is appropriate? I'm going to say this again. How do we tell whether the model that we're actually applying is basically appropriate? The only way to tell is to investigate assumptions underlying the use of a model. Every statistical model has assumptions. And I'm going to say this. A model is as good as assumption put into a model A model is as good as assumptions. Putting into a model. Now, you know what I'm trying to say? What makes a model to be great is when assumption hold. When the assumptions underlie the use of a model do not hold, you can never trust any recommendation using that model. Okay, because of that, what are we going to investigate? We're basically going to investigate assumptions of normality. Why? Because in a situation where the effect is random, right, we actually assume that that particular effect will follow a normal distribution with the mean zero and the variance of that effect. Now we need to investigate whether our normality assumption hold before we can actually trust whatever information or whatever that come out from that. And that's why you can see now random effect. I want to investigate Bash normality. What do I mean by that? Don't forget, we're looking at one of the factor in our model is Bash. Got different levels of Bash, and what we are testing, don't forget, when a factor is random, we are not testing the equality of means. You know what are we trying to do? We are trying to investigate whether the variance in the levels of this factor is significantly different from zero or not. I want you to take note of that. That's what we're testing. Okay, in the fixed effect model, we are testing equality of means, right? But in the random effect model, that's not what we are testing. The focus is on variability. The focus is on variance. We basically want to see whether the variance associated with a particular effect is significantly different from zero or not. Let me tell you this. It is only when the variance associated with a particular effect is significantly different from zero that you will be able to investigate what is the contribution of that variance to the variance of the entire system. Does that make sense? Now, we now want to investigate assumptions of normality of the Bash. Now, then we're going to use what I call a QQ plot. And that is a code on the board. Take a look at that. Okay, that's what you see, QQ plot. Okay, now we're going to generate that, and in the end, take a look at what I'm seeing now. Okay, if you look at the QQ plot, we actually if you look at the residual plot, the QQ plot, of course, if I really want to know whether the distribution is normal, of course, in the QQ plot, we actually expect most of the point to actually lie on the diagonal straight line. Okay, and we also have a residual plot to investigate assumptions of constant variance. Okay, constant variance. Now with the residual plot, that will tell us whether there's a constant variance or not. Okay, but QQ plot will enable us to know whether assumptions of normality hold. Okay, now because of that, I will quickly go into two random effects. What if in a situation I got two ANOVA and the two factors are both random? Factor A is random, factor B also random. Okay, now, of course, this is an example. This problem is actually from problem 11.2. You can check the recommended textbook. For those of you who do not know, the recommended textbook is published. Check the canvas. In fact, the current assignment, I actually extract some questions from that textbook. I refer you to the textbook, the assignment that I gave yesterday. Okay, now take a look at this problem now. Milk is tested after pasteurization to assure that it is safe to consume. The experiment was conducted, to determine the variability in test results between laboratories. Take a look at that variability between laboratories. Okay, looking at the variability between laboratories, of course, you are more or less trying to talk about the random. Now, 5 control laboratories are selected at random. Oh my God, you're selecting laboratory at random, that qualify laboratory to be a random effect. Okay, from those available in a large metropolitan area, and 4 levels of contamination are choosing at random. Oh my God, you also choose both factors at random. And that is the reason why we got two-way analysis of variance, and the each of the factor is random. Okay, now let's look at the data. Take a look at the data. We got 5 laboratories selected at random, and we got 4 samples also selected at random. Sample is, as a factor, is random. Lab as a factor is random. Does that make sense? You all know what qualify a factor to be random is when they are selected from the population. Does that make sense? So that is what makes them to be random. Okay, now don't forget, we got 2 different approaches that we normally use in estimating parameter in our model. The first approach is using the classical approach, right? But don't forget, the classical approach requires that you should understand the knowledge of algebra. I'm going to say that again. The classical approach requires that you should understand the knowledge of algebra, because the classical approach will not come with variance estimation. You will be the one that will manually, you need to solve equation to be able to get the variance of each factor. But the new approach will basically come with the variance. Now, you know what I want to do now? What am I doing now? Oh my God. What I'm doing now, I'm using the traditional approach. You see my result? The traditional approach will always give you a result that look like a fixed effect only. You are not going to have a variance component. So now take a look at this guy now. All what you need to do, if you basically want to estimate the variance, you basically need the knowledge of algebra. Does that make sense? Okay, now, and we're also going to check assumptions. If I were you, you can run all this. Okay, this is checking assumption. Okay, you are always going to have a residual plot and the normal KK plot. The first plot that I call residual plot will enable you to investigate whether there's a constant variance. Okay, while the normal QQ plot will enable you to investigate assumptions of normality. Does that make sense? And that's what you're trying to see. But I know that here I've already used a classical approach in this result. Now there's nothing like a variance component, you know that, but I'm not interested in that for now. What am I interested in? I'm interested in checking whether assumption hold. Now, because of that, I'm basically going to generate a plot. Now, merely looking at this, there's a problem. Look at the normal QQ plot. When a normal QQ plot look like that, okay, it means there's a violation of normality. Let me tell you something. If there's a violation of normality, or there's a violation of assumption, and you ignore that, then you are more or less like a judge who try a case in a wrong court. I'm going to say that again. If there's a violation of assumption and you ignore that, okay, you are more or less like a judge who tried a case in a wrong court, in the court of law. Before a case can entertain a case, that particular court must have a territorial jurisdiction. If somebody commits a crime in the state of California, that person cannot be tried in the case of Minnesota. Even though the Minnesota court was able to establish the fact that that person is guilty, let's say the Nature Harvey that is guilty, and the Minnesota court was able to establish that. Let me tell you, the fact remains that Minnesota court does not have a territorial jurisdiction, whatever decision they take is null and void. And that is the reason. That is the same thing here. Even if your model took a wrong decision, even if your model took a right decision, but it's not the assumption underlying the use of that model, it's not hold, then you cannot use that model. That's what we mean. Now, what happened here now? Oh my God, there's a violation of assumptions of normality. There's also a violation of a constant variance. Then what am I going to do? There's a problem here. Now, if there's a problem, don't forget, what have I used? I've used a classical method. There's a problem here, right? Okay, now to fix that, one of the transformation way, one of the technique to fix assumption of normality is to go by Bose-Coase transformation. That's what I'm displaying now. Bose-Coase transformation. Now, when you take a look at the lambda, right? When lambda equal to 1, you know the meaning? Lambda equal to 1 means there is no violation. I'm going to say that again. Lambda equal to 1 actually means no violation. But the moment lambda is not 1, there's a violation. I wanted to take a look at what is being displayed now. Does the 0 lies in those 3 dotted line? Okay, I wanted to take a look at what you see now. Does 0 lies in those 3 dotted line? And that is far away from 1, 2. Then it means we can actually look at the appropriate values of lambda, which is going to be negative, right? Take a look at that. Not up to -1, not even up to -5. By the time we read that, we actually got negative 0.22. Now, what is it trying? What am I going to do? The negative is 0.22. We basically want it to make a sense. We can round it up to negative 0.25. Why do we say negative 0.25? Because if I have y raised to power negative 0.25, okay, negative 0.25 is basically going to be 1 over, 0.25, which is 1 over, that is 1, I take 1 over 4, right? Which is more or less like having a square root of a square root. Does that make sense? Is it not like a square root of a square root? Let me see. Square root of this and square root of that. Does that make sense? Half times half. That would be 1 over 4, right? And of course, that's popular, square root transformation. Does that make sense? So take a look at that. Do you know what we are trying to do here? How do we face the problem? Okay. What could have the problem? It is a response variable. I'm going to say that again. Therefore, I wanted to look at the module dot transformed. What am I doing? The response variable CFU, I raise it to power what? The value of the lambda. Then I rerun the module. Initially, look at what happened. Do you see what happened? I only use CFU, response. No transformation. Can somebody tell me? What is the power of CFU here? Can somebody tell me the power? What do you think is a lambda here for CFU? Can somebody tell me for extra credit? What is that? Good job. Send me a message for extra. Okay, now some of you have been sending me messages for extra credit, like you want to apply that to meter 1. I've already done that. Okay, if you actually have extra credit and maybe you have advised me to add it to your meter 1, and your meter 1 result, if it doesn't change, please let me know. Send me a message for extra credit. Now this the response variable here is raised to power 1. It's more or less like when it is raised to power 1, there is no transformation. But right now, I'm raising it to power what? I'm raising it to power negative 0.25. How do I arrive at that? I have to go through a Bose-Coase transformation. And if I want to get a Bose-Coase transformation that work, you know what I'm going to do? take a look at the first line on this page. You're basically going to load a package, MASS, mass. Then you're going to write box, less than minus box cost, module.aov. Where do you see the module.aov? That was what you run initially that have a problem. Okay, then lambda equal to sequential. Now you can actually play with range. Most of the time, we normally start from -2 to 2. Why do we stop at 2? Can somebody tell me? Why do we stop at 2? At time, we may need to raise response to power 2, quadratic. I think we've heard about quadratic, right? So that is why we go from -2 to 2. Some may decide to say, let me go from -3 to 3. There's no problem about that. And length equal to 100, you can choose that. And that actually gives us a lambda of a negative is 0.22. But we're going to round that up to let's take that to be 0.25. Now, right now, we've already transformed the response variable right now. We will run the module. And when we rerun the module, but there's something I wanted to take notes. Initially, what was the mean square error when you have not transformed? 1, 0, 1, 7, 4, 3. That's a lot. After transforming, let's see what the mean square residual is going to be. Oh my God. Look at that. It's 0.00003. Look at that. After you have transformed the model, the mean square residual actually go down drastically. Look at that. Now we can trust this guy now. Now, let me tell you this. When you use a traditional method, is there any variance here? No variance, right? Before you can compute your variance, you got to make sure that assumption holds. I decided not to compute my variance here. Why? I cannot trust my model here. There's a violation. But after correcting the model, after fixing the model, do you know what I can do now? I can now compute my, I can compute my variance. Look at that. That's what I want to do now. But how do I know whether my intervention work? Do you know you can go back and see plot your normal QQ plot, and the normal QQ plot now is better than the one we had before. Now, based on the new model, I can now compute my variances. Does that make sense? Now, this is how, if I want to compute my variances, recall in the classical approach, I'm talking about two-way analysis of variance. Each of the factor actually is random. Interaction is also random. You need to be able to understand this. Now, in exam, midterm 2, if I ask a question like this should be part of what you're going to write in your cheat sheet. This is very important. The EMSA for factor A is that, always that. For factor B, always that. For interaction, always that. This is a situation where both factors are random. Okay? Now, you need to know what is your N. N equal to 2, observation per cell. A equal to 5 laboratories, 4 samples. Take a look at that. Oh my God, this is what I was trying to tell you before, that if you want to use a traditional method, you need to understand algebra. Is there anybody here who doesn't understand how we figure this out? Is there anyone who doesn't understand? Oh my God, I'm seeing this kind of question in midterm too. I'm seeing this kind of question in midterm too. Now, mark my words. The probability that this kind of question is going to come in midterm 2 is very close to 1. Take note of that. Is there anyone who doesn't understand how to figure this out? Whatever I find here, I just solve equation. After I use the results in the output, and at the end of the day, I was able to get all the variance. The variance of factor A, the variance of factor B, the variance of the interaction, and the variance of residual. Take a look at that. I got all the variance out. Okay, Now, why do I need to go for the new approach? Because at times, the variance that we compute using the classical approach could be negative. We cannot have a negative variance. Because of that, we normally go for the new approach. Of course, in the new approach, you don't need algebraic knowledge, right? Because the variance will come along with the outputs. But don't forget, you need to load some special packages for the new approach, LME4. Okay. Now, take a look at that now. This is how it's going to be run. You remember the other time we were dealing with a one-way analysis of variance where one factor is random. But right now, it is not only one factor that is random. It is two factors that are random. Then I'm basically going to have a lot of nested. Look at it first. Nested. Okay. One. Okay. Vertical line lab plus one vertical line sample plus one vertical line interaction. This is the code. Look at that. Okay. Now, why are we saying we're nesting? No, that's a nested, right? It means that one, what are we trying to do is, trying to say for each factor, for a particular levels of a factor, the intercept is not going to be the same. That's what we mean. Whether for factor A, for lab, for sample, for interaction. That's exactly what we mean. Let's see what happened in the end. Okay, let's see what happened in the end. Now we actually run this. What do you see? Look at the random effect. Variance estimate of the variance will come out in the new approach. You see the variances now, right? Now there's something I want you to see. If you look at the variance here in this model, okay, despite the fact that we're using a new approach, we still need to investigate absorption of normality. I'm going to say that again. Whether classical approach or the new approach, we need to investigate absorptions. Now, don't forget, we use the method of maximum likelihood, restricted maximum likelihood. Why, right? You remember when I started the other time, the method of maximum likelihood, we are assuming what distribution? We were assuming normal distribution. So which means also in the new approach, we still need to investigate absorptions of normality. Does that make sense? Now, we want to investigate absorptions of normality now. Okay, the same way we do. Okay, which I'm actually, we investigated the absorptions of normality and we realized, just like what happened in the of course, you know how to do that now. We realize there's a violation. And when there's a violation, look at what do we do in the new approach now? What do you think we do in the new approach? In the new approach, we raise the CFU to power of negative 0.25. Do you see that in the new approach? So which means since there was a violation of normality, okay, in the classical approach, there's also going to be a violation of normality in whatever approach that you use. And if you see now, what I'm fitting now, okay, when I'm fitting the new approach, I'm actually using a transformed response. What do you see? CFU, raised to power what? Negative 0.25. Okay, and that was what led to these variances here. I mean, what led to all this? And if you basically want to see, you can actually compare the variance here, the variance that you got here, with the variance that you got here. Don't forget, you got this variance after you have fixed the problem of normality using the classical approach. Let us now compare the sigma square alpha beta, the sigma square alpha, the sigma square that with this guy here. You're basically going to see they are almost the same. Okay, the classical approach, we agree with the new approach, provided there is no violation of absorptions. Okay, of course, you know the reason why we go from classical approach to the new method in the first place. There are two reasons. Number one is to save ourselves from rigorous algebraic way, because when you use it a classical approach, that will not come with the variances estimation. You need to use your algebraic knowledge to solve for the variances. That is number one reason why we go. Number two reason is that why we go from the classical to the new method is that the could have situation where variance could be negative in that of the classical. That's why we go for the the new approach. Now, you know, in the new approach, you're only going to have the variance estimation, the standard deviation, but there's not going to be p-value. You know that, right? And that you needed to load another package to have access to p-value. Do you remember? Loading a package RSRSIN. Don't forget that. I walked you through that before. And what can you see now, right? The p-value here is very, very small, which is trying to tell you, the variance of factor A, the variance of factor B, the variance of the interaction, okay, they are significantly different from zero. Okay, so take a look at that. So I think that is what I just and then just to tell you, getting the random effect, for the interaction, getting it for the lab. Of course, don't forget the assumption is that the intercept of factor A, levels in factor A will not be the same. Intercept of levels in factor B will not be the same. Intercept of levels in the interaction will not be the same. That's exactly what we're trying to show you now. They're not going to be the same. Okay, so take a look at that. Okay, now this is more or less like I basically want to investigate assumptions, whether assumption hold. I know I told you assumptions of normality, assumptions of constant variance is very, very essential. Okay, now if I'm talking about two-way analysis of variance, oh my God, there's so many assumptions to investigate. I'm actually going to investigate assumptions, the normality for lab. Don't forget, lab as a factor is a random effect. It followed normal distribution. We need to investigate that. What about sample as a factor? It follows normal distribution. That also need to be investigated. And we're also going to investigate the assumptions of the constant variance as well. Okay, now, what are you saying now? Oh my God, look at that. We are investigating the assumption of factor A, assumption of factor B, assumptions of the interaction. Don't forget, factor A is random, factor B is random, the interaction is random. When they are random, they follow normal distribution, and we basically want to investigate that. Okay, that's exactly what we're doing here. We're also going to investigate the assumptions of the constant variance and so on like that, just like what we normally investigate to see that everything looks good. Now, the last objective of the day. You remember the other time when I was talking about the fixed effect model, we talked about the effect of blocking, right? Okay, that we call that randomized complete block design, right? Okay, now let's also talk about effect of blocking. In the fixed effect that we have done before, okay, the blocking effect was fixed. What of in a situation where the blocking effect is random? I think, of course, you all know the reason why we block. When we have a heterogeneous area, and we basically want to partition the heterogeneous area into homogeneous units. Of course, we introduce a block. Now, let's take a look at the effect here. Now, here, you know what we're trying to do, okay? We're actually considering one factor, and what that factor is variety, okay? And a blocking effect, okay? The blocking effect that we're introducing is random, not fixed this time around. Okay, now let me tell you this. This is more or less like a mix effect. the main factor, variety, is fixed, but the blocking factor is random. I'm going to say that again. The main factor, variety, okay, you want to look at the effect of variety on yield, and in the process, you actually introduce a blocking effect, and the blocking effect is random. Okay, now when you actually run your ANOVA, what are you going to see? In running your ANOVA here, of course, block plus variety, right? Block plus variety, okay? And of course, you load a package for you to be able to actually, you can see the one I put, one vertical bar block. It means block, that factor is random. And when it is random, you know what I mean? I actually want block, different levels of block to have different intercepts. That's exactly what I'm introducing. But in the variety, okay, the intercept is going to be the same for all level. The slope is going to be the same for all level. Now, let's see what we got at the end of the day. Okay, let's see results. Oh my God, look at that. The variety here is fixed. The fixed, this is the way fixed result is always going to come out in R. Don't forget, how many levels of variety am I considering? 8. R will only report 7. You did not see variety 1. The variety 1 is actually, is the intercept here. Does that make sense to everyone? Now, where are you going to see block? The block is basically going to be in the random. I want you to look at the first thing that you see up there, because the block is a random effect. What you're basically going to see is going to be the variance for the block. What is the variance for the block here? 876.5. What is the variance for residual 1336.9? Take a look at that. Okay, this is the result. Okay, now, if that is the result, some other things I can actually do here is also to test whether the effect of block is whether the assumptions of normality hold for block. Don't forget, I'm actually considering a randomized complete block design. I'm considering one factor experiment, but I'm introducing block. That factor is variety, is fixed. Okay, is fixed. Now the block is random. Okay, now because of that, I need to assess whether block is normally distributed or not. Okay, I also need to investigate whether residual follow normal distribution. And not only that, I need to investigate assumptions of constant variance. And of course, that's why take a look at this now. This is a QQ plot for block. Okay, and of course, you're going to see a residual as well. So take a look at that. Okay, so there you can actually tell whether assumption hold or not. Now, the summary before I go. What is the summary of random effect model? Because today is going to be the final, this is going to be the last time we're going to talk about this, because what we are starting on Wednesday, basically going to be analysis of covariance. But let's take a look at the, the takeaway from this. Number one, there are 2 approaches when you want to fit a random effect. Number one is the classical, and the other one is the new approach. When you fit the classical approach, okay, you basically need the algebraic knowledge, because the classical approach will not come with the variance estimation. You will be the one that will solve that mathematically to be able to obtain your variance. But the new approach actually come with the variance estimation. I want you to take note of that. The classical approach work for simple balance designs, which I wanted to know. When situation is no longer balanced, there's going to be an issue. Okay. Now, the classical approach is easy to implement with AOV by equating various mean square error to the expected mean square. The classical approach may be problematic and produce a negative variance component. You know that was one of the reasons why we have to move to the new approach. Okay, what if I solve a problem and I got a negative variance? Okay, now to address the issue, a new approach involving restricted or maximum likelihood was developed to address the problems with a classical approach and to analyze of more complicated designs. Okay. Now, number 6, LMER is one of the arrow current state-of-the-art technology. Of course, so now you need to load that, right? Okay. Then number 7, p-values are not generated with LMER. You remember that? If you want to get a p-value, then you need RLRSIM. Don't forget that. Okay. Number 9, p-value for fixed effect may be obtained using the CAR package and another function to generate type 2 tests using the Ken-Ruger degree of freedom. Then number 10, mixed modules are modules that contain, of course, both fixed and random effect. I think I still have 5 minutes. I quickly want to walk you through the Ken-Ruger. You talk about Ken-Ruger. I think the Ken-Ruger is actually here. Okay, now take a look at this is a Ken-Ruger now. I actually want to test for variety effect use. And I know I load a special package CAR, right? And that is a code. Now, what that is going to analyze for you is what we call analysis of deviance table type 2-word F test with Ken-Ruger. Now, this is only going to focus on the fixed effect only for you. It's basically not going to come with the variance aspect, but the Ken-Ruger can be trusted more than the conventional approach that we use. Because you know why? It's using a type 2 kind of sum squared. So that is what that means. Is there any question? Because that is basically going to be the end of our lecture today. Any question? Before I go, I want to say this again. We are actually at the countdown to midterm 2, and I want a situation whereby the performance in the midterm 1 will be greatly improved upon. And whatever I say in this class, please make sure you take note of that. Okay. I've mentioned, I've seen so many areas in what I've presented today that will be covered in midterm 2. So today's material, and of course the material that we did before the the midterm, the spring break, they are very, very crucial. And in case you don't really understand whatever I've been saying, why can't you set up an appointment with me? Or why can't you meet me during my office hour? Like I said, tomorrow, I'm going to upload midterm 2 practice questions, just like what I did for midterm 1. Any question before I go today? I can see you guys are looking so fresh, you really enjoy your spring break. Okay, make sure you stay safe and have a lovely day. Bye for now, everyone.